Thank you all for joining me on this wonderful day. I'd like to talk about substituting units into multivariate power series, which is joint work with Mark Maza from Western University. I am Eric Postma, Math Group Manager at MapleSoft. So I'll start by talking a little bit about multivariate power series. We, of course, encounter power series in calculus as infinite sums, and sometimes they converge to a limit and sometimes not. And Maple has many tools to create these power series. So there's the series command, which will give you a finite number of terms. And there is also convert sum, which will give you a symbolic expression. And you can go back to the original by using value. Most of these tools can be convinced to deal with multivariate expressions by dealing usually with one variable at a time. So with series, it's a bit slightly messy, but I won't go into too much detail, but this is how you do it. You take the series with respect to one variable, you convert it to a polynomial, and then you take the series with respect to a different variable, and you convert it to a polynomial in that variable, and then finally you get, in this case, the answer with all the terms in degree less than 5 in both x and y. There's also the Amputator Command, which is meant to be used with multivariate expressions, and that will give you the terms of homogeneous degree of less than 5, which is usually more likely to be what you want. In this case, convert sum happens to do the right thing, but it's not necessarily meant to do that in all cases. So we might have to do the same thing we did with series. So this is dealing with power series, but we're dealing with them in a sort of a calculus sense. A formal power series is the same sort of object, but we forget about the idea of whether the series converges for certain values of x or what its limit might be. It's basically just an infinite sequence of coefficients that we can manipulate algebraically, or if it's multivariate, it's not really a sequence because there's no ordering typically. But, we have a convert formal power series command that does this, what you see here. For Maple 2021, we introduced a package called Multivariate Power Series. And the main difference with the pre-existing tools is that it is lazy. So it's set up to, you describe to it an expression that you want a formal power series for, and it then computes a bunch of coefficients, and it can compute additional coefficients fairly cheaply instead of having to start over if you decide you don't have enough precision in your answer. It also supports multivariate expressions natively. So this was described at last year's Maple conference, but I'll give you a very brief demo of what sort of things it does. So you create the power series, and now you can ask it to truncate this power series at degree 4. You can also do arithmetic with these power series and compute the result up to degree 4. If we dig a little bit into what this thing looks like on the inside, the most important part of such an object is the procedure that we specified here explicitly, which computes the dth degree homogeneous component. The result, we can examine what that looks like for this object Q that we created with these arithmetic operations. And this looks like a bit of a mess, but I happen to have access to the source code, so I can tell you that it uses preprocessor macros to do this. So this looks relatively simple. The object is asked for the homogeneous component of degree D. And it says, well, you take the homogeneous part, the d-homogeneous part of some object plus the d-homogeneous part of some other object. And the reason that that's what it does is because this is the procedure that computes homogeneous parts of power series objects defined in terms of addition, like this one. And we can dig into it a little bit more, and we see two operands. This is p itself, and this is -1 over p squared, and we can dig more into it, but we won't do that right now. Okay, so that was a very brief overview of the multivariate power series package. I want to dig a little bit deeper into the algebra background now. So we're dealing with formal power series over the complex numbers in this package in any number of variables, and this forms an algebra, which is usually denoted in this manner with double square brackets. The algebra has a unique maximal ideal, usually called curly M, and it's generated as an ideal by each of the individual variables. And you can characterize it by saying it consists of the formal power series with constant coefficient 0. So these are the power series that cannot be inverted. So you call those the non-units. So as an example, if you recall, P was defined up here as basically e to the power x plus y. That means that P minus 1 has constant coefficient 0, and that means it cannot be inverted within the domain of formal power series. So if we attempt that, we get an error message. This error message. So just to gain a little bit more intuition, for non-negative d, m to the d is generated as an ideal by all monomials of homogeneous degree d. It contains all monomials of homogeneous degree at least d. So that means that these powers form a filtration. So that means it's basically a descending sequence of ideals. M to the 0 is by definition basically the whole algebra, and it contains m, and m contains m squared, and m squared contains m cubed, etc., etc. And the intersection of all these powers of d is singleton 0. So such a filtration yields a topology, so that the neighborhoods of a power series P are of the form P plus m to the d for non-negative d. Basically, the intuition here should be that two power series are close together if they agree on many of the initial homogeneous degrees. In other words, if the first homogeneous degree at which they differ is high, then they're close together. Rephrasing it again, if you have a sequence of power series, if you want it to converge to a limit, then eventually the first d coefficients have to be constant. They can't change anymore as you continue along this sequence of power series. And that has to be true for all d. And the name that is sometimes associated with this topology is Krull, the Krull topology. I think he was German. Now, a typical multivariate power series function, the way that we've seen, for example, for this addition, the way it works is to compute a particular homogeneous component of the result. We inspect the homogeneous components of the input, and we only want to inspect finitely many of them. Otherwise, of course, we have to do infinitely much work. So for this to work, that function that is computed by this procedure would have to be continuous in the Krull topology. So if we want to compute the d homogeneous component of R, we need to know R up to its coset given by given as R plus m to the d plus 1. That's exactly what we need to know to find the dth homogeneous component and the lower homogeneous components, which we typically know already. And in order for this to be possible, to compute this knowing only finitely many components of P and Q, we have to be able to compute this from P plus M to the E and Q plus M to the F. In short, F of P plus M to the E, Q plus M to the F has to be contained in R plus M to the D plus 1 for all D. For all D, there has to be such an E and F. And this is exactly what continuity is, of course. And it's a simple exercise to show that all the algebra operations, scalar multiplication and the ring operations, addition and multiplication, are continuous, as is inversion of units. So let's talk about something that gets a bit closer to the actual subject of this talk, substituting non-units into power series. Recall the title is about substituting units, but we talked about the non-units first. So this year we wanted to add substitution of one power series into another to this package. And that's relatively straightforward, at least mathematically. If the power series we are substituting for a variable into another power series is a member of M, that is, if its constant coefficient is 0. In this case, if you want to compute the dth homogeneous component of the result, it's basically polynomial arithmetic. There is some bookkeeping overhead, but that's the idea, at least from a mathematical point of view. The univariate case we can dig into. I've written it out here. I won't. It's basically a formula known as Fadi-Bruno's formula. But I won't go into it now, given the time limitations of this talk. However, it's very clear if you dig into this derivation that you need the constant coefficient to be 0 in order for this to be a finite amount of work involving only a finite number of components of the input. So the process is continuous in the Coulomb topology, and we can implement it in multivariate power series in a fairly straightforward manner for these non-units, even if it's a little bit heavy in bookkeeping details, especially for the multivariate case, but that's life. However, this derivation breaks down completely if B0 is non-zero. So let's look at an example to illustrate this. If we have this power series x to the n over n factorial, which we would traditionally view, of course, as the power series for e to the x, and we substitute x equals b into a, we would expect to find basically the power series for e to the power x, which we can view from a traditional power series point of view and find a closed form for it, which is e times bn over n factorial times x to the n, where bn is the nth Bell number. So the first few terms look like this: e plus e times x, so e times x squared plus 5/6 e x cubed. So if this were a live presentation, I would now ask, does anybody see anything surprising in there? So you can think about that for a second, except of course you already see the answer here. There's that factor of e in there. Where does that come from? So the input power series obviously have only rational numbers as their coefficients. And now this substitution gets a transcendental number as that constant coefficient. Obviously, we can't get that with polynomial arithmetic. So again, if we take a minute to see what that constant term should be by truncating both a and b to degree d and substituting the result into itself, then it's pretty clear that the constant term basically looks like the sum of 1 over n factorial, which of course converges to e as d goes to infinity. But it has a non-zero contribution for every value of n. And that's a problem, because in this setup where we examine some finite number of coefficients of the inputs, we can't possibly implement all of them and get actually to the limit. So we have a problem. In other words, we see that substituting a unit into a power series is not continuous in control topology. However, if we have this power series and we substitute it into itself, we see that the multivariate power series package in its newest iteration, I should mention that this is the sort of work in progress version of Maple, gets exactly those numbers that we expect to find here. So the multivariate power series package must be doing something to make this work. I wonder what it is. Well, thankfully, the multivariate power series package frequently has some information beyond just that procedure to compute a homogeneous component. We initially did this mostly in order to make the objects look nice. You can see you can specify basically a closed form expression when you create a new power series, and that's used here in the typesetting of what this thing is. If you create your power series objects by specifying the procedure, then the only way that Maple can get that information is if you specify it. But many power series just come from rational functions or from algebraic combinations of things, and then Maple, of course, maintains that information itself. So we often, but not always, have that information. There are some exceptions, because the package can compute power series that there is no closed form for, or at least none that we can compute. So it's not always there, but often it is. And if both power series involved in the substitution have their closed form expression defined, then we can simply define the power series by creating the closed form expression formed by substituting b into a. And then once we have that, we can basically say, well, we can differentiate this expression and evaluate that at the origin. And if we want to find an arbitrary coefficient of the result, say x1 to the m1 ... times xn to the mn, then what we do is we take that closed form expression f and we differentiate it m1 times with respect to x1, and mn, etc., and mn times with respect to xn. And in the result, we substitute x1 equals 0, etc. And what this does is it gives us exactly, if you imagine f being given by the power series already, then this would give us that coefficient of x1 to the m1 times ... times xn to the mn multiplied by m1 factorial times ... times mn factorial. So if we divide that out, we get the right coefficients, and we find the homogeneous component by the result by adding up these coefficients multiplied by the associated monomials. Great. So problem solved, right? Well, there is a clever trick that we can do to make this more widely applicable, which is the following. So if we have two formal power series that have an associated closed form expression and some constants, some complex constants, then evaluating A at xn equals B, so substituting B for xn into A, we can write that as a sequence of two substitutions. So we can substitute xn equals xn plus C into A, and then substitute xn equals B minus C into the result. And this first substitution is of a form that's called a Taylor shift. The proof is almost trivial, but my PhD supervisor a long time ago told me whenever you give a presentation, there should always be at least one proof in it. Otherwise, it's no good. It's just like a movie. Every movie has to have one love scene. So here's the love scene of this talk. The proof is essentially trivial, but I'll run through it anyway. If you have two closed form expressions, FA and FB for A and B, the closed form expression that the above process finds for the left-hand side here is FA evaluated at xn equals FB. For the right-hand side, what it finds is, well, for this thing, it's FA evaluated at x equals x plus C. And if you evaluate that at x equals FB minus C, you get the result, which is FA evaluated at xn equals FB minus C plus C, which is, of course, the same as what we have here. And each coefficient of this power series is defined in terms of that closed form expression, and each coefficient of this power series is defined in terms of this closed form expression, so they match. So this may not seem very useful, but it is useful if we choose C appropriately, namely if we choose C equals the constant coefficient of B. So we write B equals B0 plus B minus B0, and now B minus B0 is non-unit. And that means that now for this substitution, we certainly have a closed form expression for xn plus b0, namely xn plus b0. And for the outer substitution, we don't need any closed forms because this is non-unit. So what we've gained is we only need a closed form expression for A for this to work. And what the lemma gives us is, if we choose to use that as the definition, then that definition coincides with the earlier one. I have a bunch of implementation notes that I think are interesting if you're interested in the details, but I don't have time to go into them now. So feel free to take a look at this and ask me questions. Thank you very much.